Okay, so this is actually our circles quiz, not 6-1 to 6-4 test that we took in class today on Cinco de Mayo, I think it is. So here are your answers to 1 through 9. If any of those, if you messed up on any of those, you might want to look back on the packet at page 1 where it goes into the different types of segments and etc. in a circle. On number 10 and 11, all of these pictures, all these angles in this circle are central angles. Okay? Central angles have the same measure as the arc. So for instance, this 55 is the same as arc AM. That should say 55. This 65 is the same as arc CN, etc. Okay? If MN is a diameter, sorry that I kind of drew through there, then everything on one side of it has to add up to 180. So 55 and 65 together is 120. Subtract that from 180 and you get 60 for this one. Okay, and also we have MN and AB, those two form vertical angles. So if these are 55, then this is 55 and so is this. So arc CB, you add 65 plus 55 and that gives you 120. Arc ABN, that means I go from A and I go past B to get to N. So that's all the way around here. So that's 180 plus 55. So 180 plus 55 is 235. In question 12, you needed to say this specifically. You needed to say specifically, no, because 4 squared Pythagorean theorem plus 12 squared does not equal 13 squared. It has to be a right angle here for this to be a tangent. And if it's not, that's basically what we're asking is this a right angle? If it's not a right angle, then that's not a tangent. Number 13 is the first one I saw a lot of people miss. So let's look at number 13. Number 13, it actually tells you it's a right angle here. They really didn't have to tell you that. It says YZ is tangent to circle T, so they really didn't have to put the right angle here, but we did anyway. So you know that this is a right triangle. Okay, in a right triangle, Pythagorean theorem applies. So this is r squared plus 6 squared equals the whole hypotenuse, which is r plus 3 all squared. And that's, you see where I set it up right here. R plus 3 all squared. This is the one I told you guys to be careful about when you square a binomial. This has two terms, 1, 2. That's why it's called a binomial. When you square it, you're multiplying it out like this. So that's where you FOIL. So that's r times r, which is r squared. R times 3, which is 3r. 3 times r, which is also 3r. And 3 times 3, which is 9. So when you square that, what you get is r squared plus 6r plus 9, not just r squared plus 9. And on this side, you have r squared plus 36. So the nice thing is that the r squareds will cancel. So you have 36 equals 6r plus 9. Subtract 9 from both sides, and 27 equals 6r. Divide both sides by 6, and that simplifies to 9 halves, or 4.5. It says round decimal answers to the nearest tenth, so 4.5 is fine. Okay, I think the biggest problem on that was probably squaring the binomial. This is a really, really big thing to be aware of throughout every math class you take. There are surely people sitting in calculus right now who still forget that when you square a binomial, you can't just go r squared plus 3 squared. It's very easy to forget. All right, next page. Number 14. Common tangents. Common tangents are lines that touch both circles in one point and only one point. A lot of people got these just fine. A lot of people, or several people at least, added a few extra ones. Here's one line that passes both. The line x equals 2 is a line that touches both circles in one point. Then we can also say on the other side, the line x equals negative 2 touches both circles in one point. I had some people try to add, it's like, well, if we're going to make a box, let's make it pretty and go ahead and put one on top. and one on the bottom. These are not common tangents because both of them only touch one circle. So if you put y equals 2, no, y equals 1 or y equals -6, those aren't common tangents because a common tangent has to touch both circles. Yep.
They can't cross inside the circle.
Yeah, not on this one. Yeah, if it goes into the circle at all, it's not a tangent. So you can't do one through here either because then it wouldn't be a tangent. So those are the only two, is x equals 2 and x equals -2. This one most people got just fine. You set these two sides equal and then solve and you get 7. Number 16, remember with angles, basically the rule is outside, inside, on. This vertex is on the circle. So the angle is going to be half the arc, 42. Most people got that one just fine. Then when we were talking about inscribed angles, which is what that is, one of the little properties we said, and this is on the notes page, if you have a triangle inscribed in a semicircle, or if you have a triangle drawn inside a circle so that one side of the triangle is a diameter, what kind of triangle does it have to be?
Right.
A right triangle. So this has to be 90. So that's a 90-degree angle. It makes sense because if you have, let me see if I can do this. Basically, think about extending the sides of that angle. If this is a semicircle from here to here, if that's a diameter, then this is all 180, and half of 180 is 90. So that's what's going on there. So anytime you have a triangle inscribed in a circle where one side of the triangle is a diameter, it's automatically going to be a right triangle. And then that makes x 20, because the two acute angles of a right triangle have to add up to 90. And then if x is 20, that angle intercepts z, and so 20 is half of z, so z is 40. So x is 20, and y is 90, and z is 40 on this one. Questions on that?
Never mind. Sorry.
Okay, on number 18, a few people got this one wrong. What you have to remember for this one is that opposite angles, let's start with, if you have a quadrilateral drawn inside a circle, and this was one of those theorems on our notes page. If you have a quadrilateral inside a circle, the opposite angles have to be what?
180.
Yeah, they have to be supplementary. They have to add up to 180. So 102 plus y has to be 180, so that's how I knew that was 78. And x plus 100 has to be 180, so that's how I knew this was 80. Okay, 19 is the one I said that reminds me of two spotlights. If you have an angle that intercepts an arc of the circle, and then you have another angle that intercepts the same arc of the circle, because those both intercept this part right here that's labeled y, then they're going to be the same. Because if they're both half of y, then they're the same as each other. So that's how x is 38, and if they're both half of y, 38 times 2 is 76. I think I started to write 78. But it's 76. Okay, any other questions on this page? Anything you need to look back at? All right, next page. Okay, this is where we start getting into basically the property about how if you have two chords that are the same, then the intercepted arcs are the same. I think most people got this. That means this part and this part are the same. So I'm going to subtract 360 minus 106 and then divide it by 2. And that's how you get 127. On number 21, if two chords are the same distance from the center of the circle, then what's true about them? They're equal or congruent. Okay. On number 22, measure of arc VT. Well, VW is a diameter. So everything on one side of VW is 180. And we know, because those two chords are the same, that from T to W is 55, just like W to U. So if I subtract 55 from 180, I get 125. This is one that several people who messed up on. And we did one like this as practice because I wanted to show you, you got to be careful. And I'm not even sure what happened with some of the ones that were kind of messed up.
Helen McAllister, please call 3418. Helen McAllister.
It's called 3418.
Okay, because usually when people mess up on this, it's because they're looking at these two sides and thinking they're identical. Okay, and they're not. Okay, DC goes right down through the center of this circle. So everything on one side of DC has to be 180. So if this part is 117, 180 minus 117 gives me 63 for this part. And over here, if this part is 68, 180 minus 68 gives me 112 for this part. Okay, so arc AD is 112. And because the measure of angle ADE, and I think some people just misread this and were thinking it was the arc ADE. Be careful that you know whether you're looking at an arc or an angle. So this time we're looking for the angle. So measure of angle ADE means this angle, the one with the vertex at D. So I'm trying to find half of all of this. So all of this added up is 128 plus 3 is 131. So half of 131, which gives me 65.5. Yes, ma'am.
How do you know that DC went right in half of the circle?
Well, if you didn't know that DC was a diameter, basically because it looks like one, because it looks like it goes through the center, because if you didn't know that, you didn't know anything. You wouldn't have been able to find any of this.
Okay.
Yeah. Without assuming that DC is at a diameter, you can't find any of it. Okay? Basically, that's one of those exceptions to the what it looks like rule, is if it looks like it's straight and goes through the center, then we say, yeah, that's a diameter. Kind of like up on number 22 as well. Yes, ma'am.
To find angle ADE, you said you added 68 plus 63,
And then took half. So 68 plus 63 gives me 131, doesn't it?
Yeah.
And then half of 131 should be 65.5?
Yeah.
Okay. So that's how I got that one. All right, down here, this is, again, using the outside, inside, and on. So basically, on all of these, you're looking at where the vertex is. If it's outside the circle, you're going to do half the difference between the two arcs. If it's inside the circle, you're going to do half the sum of the two arcs. And if it's on the circle, it's just half the arc. So let's start with outside. Outside, half the difference. So this one, these are my two arcs, the 113 and the 45. So I do 113 minus 45, take half, and you get 34. Same thing for number 28, because the vertex of this angle is outside the circle. I have to find this arc first. So the first thing I would do is do 360 minus 129, which gives me 231. Then it's 231 minus 129 and take half of that. And that's how you get 51. So 1/2 the difference between these two arcs. No other ones here are outside. How about on? When the angle is on, when its vertex is on the circle, the angle is half the arc. So 77 times 2 gave me x. Or on number, that's about it for here. Number 27, this angle is on, then this angle is going to be half the arc. The arc here is 216. I had several people ask me about this. That arc is 216, which means this arc is 360 minus 216. 360 minus 216 is 144. Is that right?
Mm-hmm.
Okay, so angle 2 intercepts the arc that's 144. Okay, another way you could have done that is because this is a straight line, 1 and 2 add up to 180. Okay, so you could find 1 first and say angle 1 is half of 216, and that's 108, and then subtract from 108 from 180, and that makes this 172. Okay, so either because this is 216, that's 108, and then subtract from 180 to get angle 2, or because this is 216, this arc over here that's orange on mine is 144, and then half of 144 gives you 72.
So you said if it's outside, it's
Half the difference.
And then if it's on,
It's just half because there's only one arc. If it's inside, it's half the sum. So on these, and y'all were really good on number 30, most people did not get tripped up. That's the type a lot of people do get tripped up on. On angle 1 here, the two arcs would be this one that's right in front of it, and then going backwards away from angle 1, this one back here. So half the sum of 77 and 52. On this one, if I want to find angle 1, I'd have to add this arc and take half of them. But I don't have those arcs. So the other thing I could do is I can say, let me find this angle. It's half of 114 plus 34. 114 plus 34 gives me 148. Half of 148 is 74. And once I know that this is 74, these two make a linear pair. Okay? I'll resume in the next video.